I'm going to invite my colleague Purva to introduce, and Sal is on site. Sal, you're here, right?
Thank you. So the next speaker we have is Salvatore. Sal joined the Institute for the Wireless Internet of Things at Northeastern University. He has his PhD from University of Catania, and he also serves on the technical program committee of several IEEE publications. He is one of the contributors to OpenRAN GIM. That's the first open source research platform for AI/ML applications in the OpenRAN. And his the research focus is more on the artificial intelligence and optimization for wireless network. So with that being said, Sal, the floor is yours.
Let me just share your deck, right? So this is again a little bit different type. Talking about this morning, we had how do you use open source, more like implementation side, right? So I thought this will be an interesting talk. Let me open up. So okay, this is the one, right?
Yep.
Oops. Yeah.
Enter.
Right. So I'm just opening up the slides. Let me just share it. I like the work your group has been doing. Very interesting, and it's actually contributing to the ecosystem. Come on, what is my June? No, that's not June, right?
Oh, sure.
No. This is your, right?
Yes.
Yeah. Share. Okay. All yours. About 20 minutes. Okay.
Yep. All right. Good afternoon, everyone. Thanks for being here. So thanks for the introduction. So today I'll be talking and discussing about this framework we have developed Northeast, and we have released the community. It's called OpenRAN GIM. Before going into like what you can do with OpenRAN GIM, I would like to start with why we decide to develop OpenRAN GIM and release it, so that you have an understanding of how to use it and why it's beneficial. So, oh no, oh yeah.
Let me just. Okay, I think we opened the wrong thing, right? Is it?
Yeah, maybe.
Yep. This is the one. Right, so.
Yeah, all right. Thanks. Okay, so first thing that I wanted to talk with you is what are the things that we need to take AI and bring it to production networks, specifically to OpenRAN networks and ORAN systems. So if you think about how you will do operationalize AI, the first thing you need is you need data. And we know that data, it's a very critical aspect. Most of the data has to be anonymized. It's very hard to get the data. Operators have the data, of course, but there are concerns about sharing the data. So how do we get this data? The other thing is that we need a platform so that we can design, train, and test different AI components, and we can deploy them as microservices. Because you can always train an AI model. You can get your own TensorFlow, PyTorch model. The thing is that how do you take that model, bring it to the network, and make it operational? The other thing is, how do you test the model? How do you get information about if the model is actually performing properly, if it's taking good decisions, is performing good inference, is accurate, and if it's general and can be applied to a variety of scenarios with different traffic profiles, different mobilities, and different number of users. So those are all the questions that kind of like led us to create this framework, which is called OpenRAN GIM. And this is exactly what we will be discussing today. So, so this is to the best of my knowledge, the first public available open source end-to-end OpenRAN system to develop an AI, test them, and play around with AI for OpenRAN systems. There is, you see the GitHub repository. There is also a website. The website comes with a variety of tutorials and information papers, everything you need to know about how to use OpenRAN Gym practically, how to run the code and download the code. You find information all there. And OpenRAN Gym gives you access to an end-to-end system where you have base stations, UEs, you have CUs, DUs, and RUs, you have all the base station components, you have the REC, in this case, the OpenRAN Gym release as a new real-time brick that's compliant with the ORAN specifications, comes from the ORAN software community, comes with all the interfaces you need to get the data from the base stations and to enforce the control actions that the AI is taking. And it comes with data collection capabilities, support for network slicing, and it also comes with XApps. We call them template XApps. So those are skeletons of XApps that you can customize with your own logic. So you can attach the interfaces, get the KPIs, take the decisions, and send the control decisions back to the base station. Something that I want to kind of like stress is that the architecture is primarily based on open hardware, open source component, and it's based on software. So there are four main components. The first one is the ORAN compliant real-time REC. So this is an extension of the ORAN software community REC that has been released. And this has been adapted to operate on Colosseum. And in a couple of slides, I'll tell you exactly what's Colosseum. And this is the component that you see here to the bottom left. So you have an XApp SDKs where you can customize your own XApp. Once you have your AI model has been trained, you can just put it inside the template. The template is ready and packaged as an XApp and can be deployed and tested. It also comes with all the E2 terminations that you need to operationalize the AI itself. And then there is another component, which is what we call scope. So basically, this is the actual virtualized cellular network. So it comes with software-based base stations and software-based UEs. That's based on open air interface, and it's based on SRS RAN. It's also now, I'll discuss this a little bit later, it's integrated with NS3. So you can work both with the actual radios, or you can even work with NS3 if you are familiar with simulation environments. And that's exactly what I'm saying here. But the other component is that this is something that works on actual hardware. So it's not like just simulations or emulation. There are actual radios, they're transmitting waveforms, and that's integrated with Colosseum and other variety of different testbeds. So basically what you have is an end-to-end system where you have the real-time RIC, bottom left, center part is the virtualized cellular network, and to the right, what you see there is the actual testbed where the software stack will execute. And I would like to give you some information about what is Colosseum. So this is the world's largest RF emulator. It has 256 radios. And basically what you have access to is a testbed that is available to everyone in the US that has an active NSF grant. It's also available for a fee by joining the Colosseum membership. So we have the radios. Those are 256 radios that are fully reconfigurable, and they can be configured to act either as a base station or as a UE. And the other component that you have is the channel and traffic emulator. So you can create all the EMBB, URLC, MTC traffic profile you can think of. You have like any video streaming traffic that you can want to model, anything that YouTube streaming, video streaming in general, browsing, emailing. You can generate any sort of traffic, and Colosseum will generate the traffic for you. But the most important part is actually the channel emulator. The channel emulator is basically what makes Colosseum kind of unique, because you have all the radios. And the thing is that once you have the radios and you have a testbed over the air, you can test the radios on that specific environment. With Colosseum, you can emulate a variety of different environments. For example, we have a variety of scenarios. I'm showing them like in the right part of the slide. For example, you can get GPS coordinates of base stations deployed everywhere in the world. Once you have the GPS base station, the coordinates, you can create the scenario. The scenario gets created in Colosseum. You can add mobile users, fading, obstacles, different SNR conditions. You can add anything you can think of. And the RF scenario gets created. The radio will transmit waveforms. The waveforms will go through what's called MCAM, which is the massive channel emulator. So the radios will generate waveforms that go to the channel emulator that will apply the RF conditions. So the nice thing is that you can use exactly the same software stack. You can use exactly the same radios, but you can test the AI solutions on any of all the possible RF conditions and traffic conditions you can think of. So it's one test bed to test a variety of different scenarios. And virtually there is an infinite number of those scenarios. And just to give you an idea of how easy it is to play around with OpenRAN Gym, so you can instantiate a full end-to-end ORAN compliant network with UEs, base station, neural TMRIC, XApps, and E2 interfaces that are all operating and they're working with 3 lines of code. So we have simplified completely the way those networks are deployed. It takes 3 lines of code, 1 to start the neural TMRIC, 1 to start the Gnode B and perform the subscription, 1 to start any XApp. Once you have created your own XApp with your logic, you can just like have 1 line of code to instantiate the entire thing. And it covers all of the aspects of how to test AI, how to develop AI for OpenRAN solutions. You start with collecting data with scope. You get all the KPIs every 250 milliseconds. That's the tunable parameters. You can get every 10 milliseconds, every 100 milliseconds. Once you have the data, then Colosseum also gives you access to GPUs. There is a cluster of GPUs you can use from NVIDIA. That's NVIDIA DJX. You can get the data, you can train AI inside Colosseum. Then once you have trained the AI, we have SDKs so that you can embed the AI inside the XApp. The XApp is ready, it's packaged, it's a microservice. You instantiate the neural TMRIC, and then it's 1 line of code to instantiate your XApp. It will be interfaced with the E2 interface. It will get the data and will send the data back to the base station to control the parameters. To give you an idea of how the system is working in practice, that's an XApp template. There are 2 main components you see to the left. That's what we call the service model connector. And that's where you get the KPIs. And that's where you send back any output from the AI. So this is let's say the connection module of the XApp from and to the outside world. And then there is what we call the data logic unit, which will be basically where you put the AI. Doesn't have to be necessarily AI. It can be even your own deterministic algorithm. Any logic that you can think of, you can put it there. And that includes doing inference, control, prediction, classification. Any task you can think of, you can just put the logic there. And then you can basically feed the AI with KPIs coming from the E2 termination. And then you can get out the output of the AI. To give this framework, is also a framework that we have integrated in our ODEC. So we recently got awarded with a ORAN testing integration center that's in Boston. It's actually co-located with Colosseum in the Burlington campus of Northeastern University. And OpenRAN Gym is, let's say, foundational for the testing activities we are going to do at the ODEC, which is primarily tailored apart from all the classic CU, DU, interoperability testing. This tailored that AI testing and the AI integration and the AI interoperability, looking at conflict analysis and all those problems that come with using AI with ORAN. And so when the audit basically, there is a portal, you can go there, you get access to Colosseum, you can deploy your own XApp, it's a microservice, you can deploy an OpenRAN Gym, you can get the results once the test is over. So the type of research you can do with OpenRAN Gym, I'm trying to summarize here some of the, let's say, the topics that might be of interest in general. Of course, AI-based control. So apart from just doing classification, baselining, and prediction, why don't we control the AI? All those use cases from the ORAN Alliance, you can use OpenRAN Gym to test those. That includes network slicing. You can change the scheduling profile, not the scheduling users, the profile. Like you can select if you want to do round robin or you want to do a specific weighted proportional fairness with different weights configuration at different times, depending on what's the load on the network. You can play around with traffic steering, and you can even go beyond that because you have access to IQ samples. You can play around with beamforming and RF fingerprinting and any other use case you can think of. It gives you the tools to generate data sets. without the need to care about the, let's say, the security aspects, because that's an emulated environment, so there is no sensitive information. So that's data set that you can collect, you can publish online, it's going to be open source to everyone, and there are no security concerns. You can use it for any forecasting and classification problem. You can play around with spectrum sharing, because you can create you can deploy different base stations. And then the other thing you can do is you can instantiate a radar. The radar is going to be living inside Colosseum. The waveforms are not going out of Colosseum. It's being generated, it goes to MCAM, but it stays inside Colosseum, so that you don't have to kind of like ask the FCC for approval to operate over certain frequencies. This also gives you tools for reliable AI and generalizable AI, adversarial AI. So you can create attacks to XApps and see if the XApps are reliable. You can play around with conflicts. So you can have XApps running at the same time, generating conflicting policies, and then you can determine what's the best way to handle those conflicts. And those are all things you can do with OpenRAN Gym. And to give you just like some examples, action design. So you can have XApps that can take all possible decisions to control all parameters of the base station. However, that is going to be probably a very hard and challenging task. In some cases, you might want to only focus on a subset of those actions. And for example, you can develop an XApp that, for example, in this case, I'm showing you two different XApps. One XApp only controls scheduling profiles, selecting the different weights for the proportional fairness, let's say, algorithm, or selecting a round robin. The other one is adding on top of that run slicing decisions. How many resource blocks are being assigned to each slice at any time, depending on the load on the network. And if, of course, if you look at those plots, the orange line is basically showing you, for example, that if you want to reduce buffer occupancy, which is a proxy for latency, then you want not only to control the scheduling, but also the slicing. Yep. I'm almost done. The other thing that you want to do is, for example, can we generate AI that is general? You don't want to have an XApp that works in Times Square, but when you deploy it in the Boston Common, it doesn't work. You want an XApp that works pretty much everywhere. There is a marketplace, you buy one XApp, you want that XApp to work pretty much everywhere. So can you develop AI that can handle those differences? For example, in Colosseum, with OpenRAN Gym, we have developed this XApp, and you can see that every time we activate the XApp here, which will be indicated by this arrow, no matter what's the testbed we are using, we are testing this on Colosseum, Marina, Powder, and Cosmos, which are all different platforms. The XApp is trying to prioritize the EMBB slice and give the highest throughput. Anytime we activate the XApp, no matter what's the testbed, you can always get the highest performance. And that's what you can do with Colosseum and OpenRAN Gym. You can create those scenarios. You can train AI with data coming from all those different scenarios so that the XApp is ready to operate under different conditions. Another thing you can do, online learning. So you have online learning. I'm just going to be very quickly here, but with online learning, the problem is that so you have an XApp, it's trained on a variety of subsets, so it works great on those subsets. Then there is a new scenario. For example, you deploy a new base station in an area. The XApp was not aware of that base station, and now it has to take different actions because the base station is there. So we have the distribution of actions before the deployment of the base station. So if there is a new condition, what you want to do is online fine-tuning the XApp. So you can fine-tune the XApp so that with the new base station in there, it can take different decisions that are optimal for that new deployment. You can do that with the OpenRAN Gym. You can activate the online training procedure. And if you see here, for example, I'm just like focusing on the top right plot. Whenever condition change, we started from the yellow distribution of actions. And then we see that since we activate the new training online and there is a new base station, you see that the distribution of the actions are completely different, meaning that the XApp now knows how to deal with new conditions. However, this creates problems because if you look at this plot here, I'm showing what's the performance, in this case, the throughput of the network while online training is active. If you look at the blue curve, which is by using the pre-trained model, it's fairly stable. But once you activate the training, or the online training, you see the throughput start oscillating, and there is a problem. So the thing with the question now is, how do we avoid those? And OpenRAN Gym can give you the tools to develop new solutions that avoid this problem from happening. We also, just to give you an idea, that's integrated with both NS3, OAI, and SRS. And since we talk about interoperability, I'm showing you here three consoles. So those are three different base stations. One is running SRS-LT, one is running NS3, one is running OAI. They're all connected to the same real-time rig of OpenRAN Gym at the same time. So those are three completely different protocol stacks. One is actually even a simulator. It's an emulator, the NS3, and they're all talking to the same rig at the same time. And XApps are taking decisions for all of those at the same time. So this is something that runs in real time. So the interoperability is there. This is just to give you some information about the NS3 implementation. So we have developed with Mavenir, we call it NS ORAN. So this is an open source contribution that we contributed back to the ORAN software community. So that's open source for everyone as well. And it's within the code base of the ORAN source software community. You can find all the tutorials and guidelines there. I'll stop here. And if you are interested, there is a website. You can drop me an email. You can have more information about, if you have any information that you want to have about OpenRAN Gym, feel free to ask.
Yeah, this is very nice. I guess this is open source completely. People can get it.
Everything here is open source.
Right. I know we had a security talk before. Have you looked into any of the security related emulation threats and all those?
So we have looked at some security problems from the AI perspective. So how to protect the AI from attacks where the attack is coming from the KPIs, like adversarial AI, where an attacker generates KPIs, which are not actually reliable as they're not representing the channel, the conditions at that moment. And we have designed some solution like using autoencoders that protect the AI from these noisy and adversarial attacks. And that's one of the security aspects we are looking. We're not looking exactly at the zero trust part, but how to secure the AI, that's one of the focus of the group.
There's one more question in the chat. What are, if any, cost or other restriction to access this OpenRAN Gym? Is there a specific point of contact URL? I think you already provided that.
Can you,
right?
I don't know, can I open this here? I don't see, oh. What are the costs of other restrictions?
I think they're
okay,
asking about the accessibility,
Yeah, so I mean, the software is open source. And if you want, just you can drop me an email and we can take that offline. But everything is open source.
Yeah, thank you. So we just